Um, so first things first, before we forget, regarding logistics, so we've got homework that's due today, right? So don't forget about that. It's due tonight at midnight or 11:59. And then something we haven't talked about is our first exam. So that's coming up a week from Thursday. So it'll cover, I mean, everything we've seen so far, plus then anything that we cover this week. So up until the next lecture, and then probably a week from today we'll do some review, some extra practice, but it'll be it'll be up until what we see this time around. I may assign a homework either tomorrow or maybe I'll assign it on Thursday after we do these two lectures, just covering this new content. So just to let you know, that's coming up. For that, if you are here in the classroom, we'll just have our exam here in the usual class time. If you are remote, you'll do the exam remotely. I'll post it on Canvas at the same time. And there's some protocols that I'll link you to that the college put together as to with if you're taking an exam remotely. Essentially, you need to set up your camera a certain way so that we can see your computer, we can see your workspace. Just to know that you're not going into Chegg or whatever in the meantime and asking, posting problems there. So that's the basic setup there. Yeah. So other than that, let's get into it. So we're starting a new sort of unit today. So it's we've gone over all these different types of systems, and what we're going to do is whether it's whatever type of system it is, trying to figure out can we find out the output based on the system itself and based on the input. So that's going to be our goals. Um, we call this analyzing a system, which is again based on inputs, based on what we know about the system. Can I then figure out my output? So that's going to be my main objective as I go into most of this next unit. So let me switch here to my um, piece of paper here. Just a sec. Alrighty. So let's go in here. So before we dive into some of that, I want to talk about system representation. So how do we, if we're trying to find out how a system behaves, what its output is, what tools do we have available so as to represent the system? So there's multiple ways to look at it, and our main tool here has been our little block diagram where we've got x of t as our input, y of t as our output. And we know that's, good old trusty block diagram is a great way to begin asking ourselves how something works, right? So we need to identify what's feeding it and what are we getting out of it. So our goal, again, is going to be to figure out this thing based on this. And again, that like the nice thing is that's going to apply across many different applications, across whether it's electrical, mechanical systems, whatever, these techniques are going to work. Now, there's a couple of different ways that once we start to write the equations, a couple of different approaches we can take. So these two main approaches are, one is going to be time-based, the other is going to be frequency-based. So there, and I wrote the word duality because these two are going to be connected. Any system can be expressed from the point of view of time or from the point of view of frequency. Okay, so time domain can be one way to represent systems or frequency. So what do I mean by that? So time domain, you guys can see it here, like, well, I've got x of t, I got y of t. Essentially, we've got signals that are evolving through time. So you might think, well, if I have some sort of equation that still with t as my variable relates x and y, that would be one way to express things in terms of time. And that might be the most intuitive way in many ways. However, there's been other systems, for example, when we talked about the equalizer, the audio equalizer, we said, well, we want our audio equalizer to have, for example, a bass filter that's going to take all the high-pitched sounds and remove them. and it's going to keep all the low pitch sounds, or or a treble filter that's going to keep the high pitched ones and it's going to reject the low pitched ones. To express that from the point of view of time is really difficult. You can, but it's really hard. It is much more intuitive to think of it in terms of frequency, because pitch is connected to frequency. So if you think higher pitch, you think higher frequency. So if you have a description that's frequency based, you can probably express that system, those filters, a little bit better. And it turns out for a lot of different systems, thinking in terms of frequency makes a lot more sense. For all telecommunication systems, for example, with radio, when you're tuning into a particular station, you're tuning into 88.3, and you want to hear that campus radio. Essentially, what you're doing is you are setting up a system so that it's selecting a specific frequency and rejecting all other frequencies that are out there. So this is all going to be a frequency-based expression of it. So all these things surrounding audio, surrounding communications, make a lot more sense to express here with frequency. And even things that might not be so obvious, even things like motors or, expressing, I don't know, other mechanical systems, you can also think from the point of view of frequency. It's just going to be that any system can be expressed in either way, but sometimes it's easier here, sometimes it's easier here. Now, for each of them, there's going to be a couple of different ways we can do it. In the time domain, our most go-to, our go-to type of system representation is going to be a differential equation. So if you already took that class, you know a lot about diffie-qs. Here are, unlike the math course that you took, where you would go into proofs for existence of solutions and things like that, here it's very much about, we want to find that out, but we want to use a differential equation just in a very targeted way, in an applied way, to find out my output of my system. And we'll go over how to do that. Then on the frequency side, we've got this other thing called a transfer function. So rather than your diffie-qs, you can use this other expression that's all based on frequency. And after the first exam, we'll switch over to this frequency domain and explore that. But we're actually going to start here with those differential equations and working through them in time. There's a couple other ways that you can represent systems. So there's on the time side of things, you've got this state space representation, and that's all based on matrices. So for those of you that are going to be in the controls class next semester, which is a lot of you, you're going to learn about state space representation in that one. We're not going to use it a lot this semester, but next semester we will. And frequency response, same thing. We might briefly go into it in this semester, but it's going to show up more next semester. So these are two other like alternate ways. I mean, these are all ways of representing the same physical system. It could be the same engineering system. And these are all, think of them as different tools that we can have to represent our systems the best way possible. So again, we're going to start here. We're going to start with diffie-qs for our first one. And then, if you love diffie-qs, you're going to be like, okay, great. Like, I'm glad that that's coming in handy. If not, there's these alternate ways to do it. So we're gonna explore a few different ones. Okay. Nothing is trivial, my friend. Well, I'll do my best, Scott, to make sure that I give you. No, it's not. It is really not. It's true. So. We'll tell you. It's all good. It's all good. We can let go of that trauma pretty soon. So let's look at using differential equations to analyze systems. So let's go into it this way. So I mentioned the word we were going to use was analyze. So and we'll actually explore this word a little bit more clearly. But our goal analysis is going to be about identifying how a system works. And in particular, how I get my output. So it's going to be analysis of Now, notice I wrote LTI. LTI, as a reminder, was linear in time invariant. So you guys know that from system classifications. So if systems are not LTI, if they're nonlinear or they're time variant, the math gets a lot more complicated. So in this class, we're going to just cover LTI. Usually we start with LTI systems, and if they're nonlinear, you've got to do some added level mathematics, time variant. You got to do some. Again, this would be more like grad school level math to be able to cope with that. So we're going to start with LTI systems with this time domain approach of using mainly differential equations. All right, so let's get into this idea. What do we mean by analysis? Analysis means, in our context, given a system and its initial conditions. So we want to know whether the system was at rest, whether it was in motion, whether there were voltage charges up there or not. So given a system and its initial conditions and an input, so if you know your system and you know your input signal and you know where it started, can we determine the output? All right, so that's what analyzing a system means. Okay, so that's going to be our main goal through a lot of those classes. Given a system, given initial conditions, given an input, can we determine the output? All right, so again, we've got our little go-to block. So we've got this thing is given to us. We've got some description of system G. We said it might be in the differential equation form, and this is what we're trying to find here, is our Y. So let's start with this example. Let's do this through an example. So I'll slide down. So there we go. So let's say we've got right here a differential equation where Y is my output and X is my input. What this is telling me is that this relationship, this differential equation, captures how my system works. And again, it might be a motor where this is your output and this is your input. It might be an electrical system, what have you. But as long as you've got these dynamics, you've got these derivatives here on the left, you got a derivative also on the right. So we've got a relationship there between X and Y, but captured in differential equation form. So the question is going to be, how can we break that down? How can we, from there, pick out that Y of t? All right. So there's, fortunately, for situations like this, a fairly straightforward procedure to do it. And we'll go over it. We'll go over it together. So again, we wanna find out the output. Okay. So what we're going to do is break up that output into two parts. Our Y of t is going to we're going to break it up into these two parts, ZIR and ZSR. And we're going to find out those two parts of the output independently, then we add them together, and that's going to be our total output. So what are those ZIR and ZSR? So let me slide over here. So my Y of t is my full output, right? Y of t is my full output. Okay. Then this ZIR is known as, well, ZIR stands for zero input response. Zero input response. So what we're going to do here for ZIR is we're going to assume we don't have any external input. So we're going to assume that I'm not feeding the system anything extra, X of t equals 0. And this is going to be like the part of the output due just to those initial conditions. Output due to initial conditions. Okay, so zero input response is going to be assuming the input is 0. And what is that component of the output that's just due to those initial conditions? So again, what do I mean by this in a practical engineering sense? If your circuit, or if your system is a circuit, as an example, these initial conditions might be some initial charges, some initial voltages that you had in your system prior to time equals 0. So prior to you checking the system or whatever. If you had some capacitors that were pre-charged, you might have had some inductors that were already had some initial current, that is going to be an initial condition. Or in a mechanical system, if the system was not at rest at t equals 0, then that would be an initial condition that's different from 0 there. And so the question would be, if I had those initial conditions and I just kind of let my system run, what's my output going to be as a consequence of those initial conditions? The other part, as you might guess, is going to be due to the input. So for ZSR is going to be known as zero state response, zero state. So it's kind of backward. Where like here, on the one on the left, we had 0 input and everything was due to initial conditions. Here it's the opposite. We're gonna assume that the initial conditions were 0. That is to say, we're gonna assume that the system was at rest. We're gonna assume that there was no like pre-charges or anything like that. The system was just as quiet and well behaved as possible by itself. And then we did apply an input. So here we want to see how much our input is responsible for. Output's going to be just due to input. And so at the end of the day, we're going to add up those two parts, the part that's due to the initial conditions and the part that's due to the input itself. We add those two together and we get our full output that way. All right, so that's going to be our general approach to this. So we'll start with this one here. We'll start with a ZIR, and there's kind of a step-by-step method to do that, and then we'll look at the ZSR in the next class. All right. Let's start here. So let's find the ZIR, and this is the same example as before. So you don't have to recopy it if you don't want. But what I did add there was initial condition values. So you can add those.
What's the second one say?
Yes, indeed. So notice these initial conditions. What are they? So initial condition. One is y of 0 equal to 2. So essentially, what was my output at time equals 0? And what was the derivative of the output, y dot of 0? In this case, it was equal to 4. Now, notice I have 2 initial conditions. That is going to suffice for a problem like this. Why do you think we need 2? Any thoughts on why not? Yeah, could I have just solved it with just the 1? Could I would I need some extra conditions? Yes, Nathan. It would be, yeah, you would not be able to find a precise solution with just 1. It's true, there would be too many unknowns. And why is that? Like, why 2 exactly?
The second degree differential equation.
Exactly right. So it's going to be due to the second degree right here. So if you had a 3rd degree differential equation, you would need 3 initial conditions. If you had a d to the 4 here, you would need 4 initial conditions. But so for example, here we have this order 2 here, and so we need 2 initial conditions. There we go. So first thing we're going to do is use a new notation that's for this type of approach. It's going to be really nice and practical. Again, what you're going to see as we tackle these differential equations here, it's just going to be a lot more direct than probably most of the methods you saw in your DiffyQ class, where you needed to prove why everything was valid. Here, we're engineers. We're not necessarily math majors, so we just want, if there's a method that works, hey, we're going to follow that method. And one of the most practical ways we can do it is by starting by replacing this notation of dyt dt, which is, a little bit cumbersome. We know this is a derivative, but we'll do this d times y. So d is going to be your differential operator, capital D. And it looks like a product. We know it's actually, this means that we're deriving, but we're just putting that big D in front, like that. So as you might guess, if you do second derivative, if you have second derivative of y with respect to t, we're going to use the notation d squared, and so on and so forth. So if you have, 10th, d10, dt10, we're going to call it, d to the 10th power, and so on. So the nice thing is that then we're going to be able to rewrite a differential equation in a polynomial and algebraic form. So let's do that. Let's rewrite the differential equation above using that d operator, and I'll give you a few seconds to do that. So the one above with that one right there. Let's see if you can write it and perhaps simplify it by using that d operator. Okay. So it's nothing too fancy here. We're just replacing those derivatives with the d times. So we should get that right there. So hopefully that matches what you have on your paper. So you can confirm your work there and let me know if there's any questions there. But I see people saying looks good. Great. All right. So one of the things that jumps out right away, notice that actually we can factor out this y on the left and we can factor out the x on the right. So let's go ahead and do that. We're going to get this d squared plus 5d plus 4 times y equals d plus 3 times x, right? So why not? I mean, at this point, that's the nice thing where it looks like an algebraic multiplication, so we can factor out. So essentially, we've got a polynomial here times y and a polynomial times x. So in general, let's call them this q of d for the one on the left, the one with y, and p of d right there for the one on the right, the one with x. Now the q of d has a very special name. That's your characteristic polynomial. Characteristic polynomial is going to be that q of d. So the one that goes along with your output. And so you can summarize the whole equation this way. You can just say, that thing that was your, big old nasty differential equation with second derivatives and all that. It's really just a polynomial and another polynomial. So q of d times y equals p of d times x. All right. And again, the one on the left is your characteristic polynomial. That's going to be, in terms of this one versus this one, the one that's along with the y is going to be driving most of the behavior of your system. That's going to be a more important one. Okay. So another important little note here. So q of d, the one on the left side, the one corresponding to y, is going to be of order big N. And P of D, the one on the right, is of order big M. So if, let's say, so notice I've got the note here, N needs to be greater or equal to M. Let's say here for practical engineering systems. For practical engineering systems, N needs to be greater or equal to M. If you run into a situation where this is not met, where N is smaller, that's going to be a system that doesn't work in practice. It's not realizable in practice. You're going to run into causality issues, actually. It's going to be a non-causal system. If you remember non-causal systems, your output's going to work out, or it's going to need information from the future, so you can't really bring that to practice. So in order to realize this in practice, you need to make sure that this one here on the left has a higher order, or at least equal to the one on the right. Okay. So that notation we're going to use to find our y of t. Let's go over here. And I'll say recall. So we're just trying to find the zero input response. So for a zero input, we're assuming our input to be zero, right? So recall for ZIR, zero input response, x of t, which is my input, is equal to 0. Okay. So if I have that equation, q of d times y equals p of d times x, well, x is 0. So this whole thing on the right is going to be equal to 0. So we can write that. Q of d times y equals 0. So our equation is getting simpler and simpler. Now we're going to do a little change of variable next. Just this might not seem like much. It might seem like, you know, a semantics type of thing. But instead of having d as my variable, I'm going to put lambda there. It's still the exact same polynomial. It's still my same characteristic polynomial, but instead of d, I'm going to have lambda. That's my next step. And so I end up with this characteristic equation right here, q of lambda equals 0. Now, the reason we simplify this is if we look at the line above, q of lambda times y equals 0, essentially for this to hold true, either y is equal 0 or q of lambda is equal 0. Now, if y is equal to 0, like that's your degenerate response, like it's the simplest possible one, but you're getting nothing interesting at all. So for it to be true for all inputs in all cases, we want to focus, we assume that this is not the case, and so we focus on this part right here, q of lambda equals 0. Okay, so this is going to be the equation that we're going to try to solve. Remember, this q of lambda is just a polynomial, so at this point, all we're solving is a polynomial. All right, so if we solve that polynomial, we're going to get values lambda 1, lambda 2, etc. So if it's order 2, you would get just these two. If it's of order 4, you would get lambda 1, lambda 2, lambda 3, lambda 4. Those lambdas that you get there are known as characteristic values, or also known as eigenvalues. Characteristic values or eigenvalues. Yes, Peyton.
So is this going to be like a similar process to finding eigenvalues like in the
Yeah.
Okay.
Yep. Pretty similar. And again, there's multiple ways to do it. But depending on how you learned it there, this might be something you already know, or it might be a slightly different method to get there. But yeah, we're going to get those eigenvalues there for lambda 1, lambda 1, lambda 2. Those eigenvalues are going to give me then the whole response of the system. So let me show you what I got there. So let's go little by little. So let's, based on my eigenvalues, I'm gonna write my y of t, which is my general ZIR. And I'll call, I'll put a little like O right there for, this is gonna be for 0 input. So my general ZIR, let's call it y0t. So it's going to be of this form every single time. It's always going to be C1 e to the lambda 1t, C1 e to the lambda 1t, plus C2 e to the lambda 2t, and so on. So again, if you have more lambdas here, all the way up to lambda n, whatever, you would have C to the n e to the lambda nt. Okay. Now, the way we built this is each of the lambdas, so lambda 1 generated this term right here. If you have lambda 1, it's going to generate this e to the lambda 1t. Your lambda 2 generated this term right here, e to the lambda 2t. Now those terms, e to the lambda 1, e to the lambda 2t, they're known as your characteristic modes of your system. characteristic modes. It's going to be, the modes are just this part, e to the lambda 1t, e to the lambda 2t. Now, what I wrote here on the left is the characteristic modes determine system behavior. Now, system behavior might be determined by other things. Other things might affect it, but your characteristic modes are the single most important thing in terms of determining system behavior. So if you want to find out whether something is stable or not, if you want to find out whether it blows up, whether it has any oscillations, these characteristic modes right here are going to be what tell you everything. All right. Now, a few things of note. So you might recall, well, there might be some of you that are like, what do you mean? Do I get like an exponential every single time? The answer is yes. Exponential is going to work every single time for this type of differential equation with constant coefficients. It's always going to be these exponentials. Now, as you guys know from a few lectures ago, an exponential, there's going to be many things that don't look like an exponential that are exponential. So a sine or cosine is going to be one form of exponential. A constant's another form of exponential. Something that has oscillations like a sine or cosine and either expands or contracts, that's also going to be a type of exponential. Of course, it's all going to be depending here on your lambda 1 and lambda 2. So if these things are complex numbers, then you might have those oscillations. So yeah, so what I'm saying is like, it looks like, oh, this is always exponential. Yes, but you might have also those other behaviors because of those different variants of what an exponential can look like, as we saw from chapter 1. The other thing is like, wait a minute, like why is it always exponential? Like, where does this come from? So again, we're not going to go into the full demonstration here. We're more targeted towards finding our output, but where this really comes from is in a differential equation, you want to take signals that if you derive them, the derivatives keep showing up, the same term hopefully keeps showing up itself. So if you have, just real quick, so shifting back to this one. So like here, if I've got a certain signal, here I've got the derivative of it, here I've got the second derivative, here I have an input, and here I've got the derivative of the input. So the only signal where like if I derive it, it keeps showing up in the same form is the exponential. So that's why it's going to be my go-to for this type of situation. Again, you probably did proofs as to why that works in your DiffyQ class, but over here we know that to be the case. So the last thing is you got every mode has a constant in front of it. So it's going to have a constant C1, constant C2 like that. And those are going to be constants to be determined. And we're going to determine them based on those initial conditions that we were given. All right. So that's our little method. It's going to be that every single time. So let's go through an example here together. So I mentioned, yeah, to find the constants, use those initial conditions. Okay. So let's resume that example. So let's continue that example. We had Q of D from what we wrote before. Yeah, we wrote this. It was D squared plus 5D plus 4. Right, so that was the characteristic polynomial that we found. From there, my characteristic equation is going to be this one. It's just taking that, replacing D's for lambdas, and making it equal to 0. So I get Q of lambda. Lambda squared plus 5 lambda plus 4 is equal to 0. Okay, so nothing too fancy there. It's going to be my characteristic equation for my system. From there, I would factor out the characteristic equation. From there, I would find my lambda 1, lambda 2. Notice that it's going to be, yeah, -4, -1 is going to be the values of lambda that make this equal to 0. So simply by factoring that, I get them. So I've got my lambda 1, lambda 2. Based on my characteristic values, I can get my characteristic modes. So notice my lambda 1 generates e to the lambda minus 4t, and lambda 2 minus 1 e to the minus 1t. Yes, Nate?
Is there a reason why -4 is -1, or is it be switched?
Interchangeable. Yep. So Nathan there, yeah. So he asked, could I call this lambda 2 and lambda 1 the other way, but they're interchangeable. All right, so you got those modes. And so finally, I end up with this y of t right there. Y of t is c1 e to the minus 4t plus c2 e to the minus t. Okay. Now, the last thing that we need to do is find the c1 and c2. For that one, we'll use those initial conditions. So I'll do this in the next step. Just to let you know, to find those initial conditions, we'll need to take the derivative of y of t. That's going to be necessary. So take a second to do this. I'll give you a second to take the derivative of this to find y dot of t. And I'll show you what I got. So I'll show you my answer there for the derivative. Notice it's the derivative of e to the minus 4t is itself, but then I got to apply chain rule, so I just multiply by minus 4 in the front. And then same here for my e to the minus t term, the derivative is the same thing, but I apply chain rule, so I multiply by -1. And so I get that. All right. So at that point, I have my y of t and my y dot t ready. From there, let me, do this. So finally, we want to find C1 and C2. With these initial conditions right here. So we want to find C1 and C2. Okay, find C1 and C2. And so we know we were given by the problem that these were my two initial conditions. Y0 equal 2, y dot of 0 equal 4. Gladly, I know what y and y dot are. So from here, I would just evaluate each of them at 0. So for my y of 0, it's going to be c1 e to the 0 plus c2 e to the 0. And the other one, which I, after getting the derivative, is minus 4c1 e to the 0 minus c2 e to the 0. Right, so I'm just evaluating my y of t at t equals 0 and my y dot at t equals 0 as well. Gladly, e to the 0 is equal to 1, so this is going to go away. All these e to the 0s go away. Yes, this stays. C1 stays. So from there, after a little simplification, I got C1 plus C2 equal to 2, because this was my initial condition. And then from the other one, simplifying, again, minus 4C1 minus C2 equal 4. That was my second initial condition right there. From there, you got two equations, two unknowns. And I did the algebra right here. If you want to just, like or something like that, if you want to just remember how to do it, what I did was I took the top equation and I solved for C2 from the top equation. Then I plugged in the top equation into the bottom one. So I have minus 4C1 minus, and then quantity 2 minus C1 equal 4. from there, you don't have to like copy all the lines down. It's just a simple two equations, two unknowns. So you can finish this out on your own. From there, I get my C1 equal -2. And then plugging that back into the first one, I get C2 equal to 4. And so finally, my ZIR is the following. Let's call it Y0T. My ZIR is going to be -2 e to the 4t plus 4 e to the -t. Okay, so you'll notice it's one thing that I added to the whole thing. I added a u of t there at the end, and this is for causality purposes. So in practical engineering systems, typically we care about t greater than 0. We want to make sure that everything is nice and causal. To make sure that everything is nice and causal, just, we could specify t greater than 0, or just multiply everything by u of t. And so this is going to keep everything on the right side only. So that's why I multiplied that there at the end. But yeah, this would be your behavior. Now, notice that if someone asked you, for example, now that you have that system, can you tell me whether it was stable or not? Well, you would look at these characteristic modes and see that you've got this e to the -4t, e to the -t. As time goes to infinity, those are getting smaller and smaller, right? So they're decaying exponentially. Therefore, the system is going to be nice and stable. Good. If you had e to the positive something t, then you know it's going to be like going out of control and becoming vivo unstable. All right, so that's a nice example there with the whole process. So let me give you one to try out on your own. I'll let you get started on your own, and after a minute, I'll send you an invite for a breakout room. I'll just do 2 breakout rooms, one for folks in the class and one for folks who aren't, and you can check in and see that you got the same answer. Let's try this one out. Okay. So there's your example right there. It's another second derivative. And I would like you to tell me the following things. All right, folks, so I'll send out the invitation to the breakout room, so feel free to check into that, and you can check in with your friend and see whether you're getting the same answer. Over here, I didn't send you a breakout room invitation, but it's all good. You can check in with the folks who are next to you. And again, as you're going through each of those steps, you want to make sure, wait a minute, did we get the same characteristic polynomial equation, etc. You can check in with your friends, and then hopefully you'll get the same ZIR.
All right.
All right, I'm gonna bring those other guys back.
Welcome back, other people.
They're not
that
back
aren't
yet. They're not back yet. It's gonna take another minute.
Now, this is pod racing. Star Wars, no.
I
I
know
understood the reference. I just don't see
the connection.
I don't know either. It's just so quiet. I just wanted to say something random. That was the first thing that came to my head. Gotcha.
All righty, folks. So over here, people are making random quotes that I have no understanding of. So the Phantom Menace, yes. Okay. But what is okay?
Horrible movie. After the pod race.
Yeah.
Or not after the pod race. During the pod race.
Sorry, yeah, just like that. This is pod racing.
That's right.
Oh, it's still
Yeah, yeah.
It's just the funniest one.
So yeah, people here, yeah, quoting Star Wars, and that's yeah, that was not. I think it was such a bad one that I probably blocked out from my memory.
Oh, the Jar Jar Binks is the best character.
Yeah, it's fantastic indeed. So yeah, apparently my class here is getting compared to the worst Star Wars movie, but
I didn't get a connection. Some people are
yeah. No, it's
saying. I don't know who was
it's rough.
saying that it was the worst Star Wars movie,
It's a pretty bad one. That one and Attack of the Clones are both pretty bad, right? I mean, my personal favorite, Rogue One. That was an excellent one. Fantastic. Fantastic. All right, so let's get back into it. So this, hopefully y'all got this for your characteristic polynomial, lambda squared plus 3 lambda plus 2. From there, lambda squared plus 3 lambda plus 2 equals 0 would be your characteristic equation. Characteristic values would be factoring that. And so you've got your lambda 1, lambda 2, minus 2 and minus 1, or minus 1 and minus 2, doesn't really matter. Characteristic modes, hopefully you got that. The e to the minus 2 generates e to the minus, or the minus 2 generates e to the minus 2t, minus 1 generates e to the minus t. So that's your 2 modes. From there, this was the full ZIR that I got right there. So e to the minus 2t and e to the minus t show up there. And then I had as my constant C1 and C2, 5 and minus 5 based on my initial conditions, and with the U of t there at the end to make it nice and causal. All right, so did y'all get that here? Yep, good, okay. And hopefully y'all at home got the same answer, or we're headed in the same direction. All right, so let's do a quick variant for, I guess one slight complication you might run into when you do this type of work is when you have your eigenvalues show up repeated. So that's going to be slightly different. So if you've got your lambda 1, lambda 2, and all that, but they show up more than once, what do we do in the case of repeated eigenvalues? So if lambda shows up twice, if lambda repeats twice, it's going to produce 2 different modes, e to the lambda t and t e to the lambda t. So this is essentially, you've got two eigenvalues that are both at the same spot. So rather than just show e to the lambda t and t, like basically the second one is going to show up there with a t. So watch out for that. If you have it show up multiple times, so if it repeats, in this case, I wrote r times. So if you've got lambda showing up r times, then it's going to generate the following modes: e to the lambda t, e to the lambda t, all the way to tr minus 1 e to the lambda t. So each repeat is going to generate those extra terms. So notice that two terms generate two modes, r terms generate r modes, and it's in this fashion right there that you would see them show up. And then as for your response, it would have this shape right here. So your y of t corresponding to that. Notice we're going to have the e to the lambda t there, because that's going to show up as a factor in all of my terms. And then I can factor out the rest. So it's going to be c1 e to the lambda t, and c2t e to the lambda t, all the way up to a tr minus 1 e to the lambda t. Okay. Now, if you have some that repeat and some that don't, the ones that don't are each going to generate one term, and only the ones that repeat are going to generate as many terms as they need to. Okay. So let's do an example where you might run into that situation, and I'll let you try this in groups. So let me show that right there. So you got another second derivative right there, plus 6 dy dt plus 9, and 3 dx dt plus 5. And these are my initial conditions down here, y0 equals 3, y dot 0 equals minus 7. So I'll send you an invite to the same breakout room as before. Feel free to first copy this down and join the breakout room when you're ready. And then we'll check in here in like 5 minutes or so to make sure that everybody got the same answer. Feel free to check in when you need to. No problem. Some of you are still working, but some of you are done. So even if you're still working, now might be a good time to just check in with a friend, see that you're so far you have the same steps. All right, I'm gonna bring the other folks back. Okay, folks, so let's check in with this one together. So as we're going through the process of finding the different things, let's see if we got the same thing. So it's, again, same sort of step-by-step, characteristic polynomial, then equations, then values, then modes, and then my full ZIR. So here's what I have here. I turned the stuff on the left into this polynomial right here, d squared plus 6d plus 9. From there, my characteristic equation is going to be this one, lambda squared plus 6 lambda plus 9 equals 0. And from there, my lambda 1 and 2 are both equal to -3, right? So my modes are going to be e to the minus 3t and t e to the minus 3t. All right. From there, my ZIR is going to be this one. So this, I skipped a step here to find my C1 and C2, but I think it's going to be the same process as before, where you would write the general with C1 and C2. You would derive, do two equations, two unknowns, to find these values of 3 and 2 right there for your C1 and C2. That gives you your full ZIR, Y0t equals this thing right here times the u of t at the end. Notice then your characteristic modes again are this one, e to the minus 3t and t e to the minus 3t. Question, do you guys think that this one is going to be stable as well or not? Looking at that output. So this one might be a little tricky because you've got that t in the front, right? You got the t in the front that, to me, this t makes it look unstable as you go to t infinity. But some people are saying, wait a minute now, you're multiplying here by this exponential that's going down to 0, right? So it is one of those situations where this term is indeed blowing up, but this one is bringing it down. And when you're in this type of situation, as you might remember from calc, the exponential is the strongest term. So exponential is going to win over any of the polynomial terms. So while this is trying to bring it up, this is trying to bring it down, the exponential wins, so it is going to successfully bring it down, so it is going to be stable. To give you a preview, anytime, or this is going to be clear in future chapters, but anytime you see characteristic values that are all negative, it's usually going to be, you can guarantee that it's going to be stable, even if they're repeated. So as long as they're all negative, you're going to be okay. Yeah, so that's the variant there with repeated eigenvalues. The other thing that might be a little bit tricky, we're not going to do an example right now, but there's one in the textbook that I'll point you guys to, is when the eigenvalues that you get, instead of getting just -3 or whatever, where you get complex numbers. So you can definitely get complex numbers there. And then you can still go through the exact same process. The math just gets a little bit different because you're using complex numbers, that's all. Alrighty, so that's where I got with the other class. So let's leave it right here. In the next class on Thursday, we'll go over the second part, the zero state response. Great. All right, folks, I'll see y'all later.
I looked at it, but